Hello everyone, my name is Amir Mazaheri and I'm here today to present my work Visual Text Correction, which will be published in ECCV 2018. So let's first define the problem. What is visual text correction? So the input to this problem is a video and an inaccurate description about the video, like this sentence. Someone shakes his hand. So as you can see, there is no hand in the video. So it's an inaccurate sentence. So the output is a detected inaccuracy, which we want to say the word hand is inaccurate, and an accurate word to suggest to replace the inaccurate word and make the sentence accurate. Someone shakes his head. So what is an inaccuracy? So generally inaccuracy is an inconsistency in a sentence. So it can be a textual inconsistency, like grammatical error, or it can be a contextual inconsistency inside the sentence, like somebody is swimming in a car. The sentence is inconsistent, right? Or the text can be inconsistent with the video context, like our example. So our proposed approach has two main modules. The first one is inaccuracy detection module, which takes the sentence and the video and it detects the inaccurate word in the sentence. The second module is the correct word prediction, which gets the inaccurate word in the sentence and suggests an accurate word to replace the inaccurate word and make the sentence accurate. So let's start with the inaccuracy detection module. So the role of this module is to return the index of the inaccurate word. The indices are between 1 to n, assuming that the sentence has n words. And the inputs are an inaccurate sentence, we show it with S tilde, and the video. So our module has 3 submodules. One of them is detection by reconstruction formulation, textual encoding, and gated visual bias. So let's start with the detection by reconstruction. So to get the inaccuracy scores of the words of the word T in the sentence, we need the reconstructed word vector x hat T of that particular word, the actual word vector of that word xt, and we compute the distance between these two vectors by normalizing each of them, an element-wise product, and a trainable distance metric, which gives us an scalar as the inaccuracy score for the word T. So let's look at the text encoding part. To encode the inaccurate sentence, we use convolutional n-grams to capture the short-term dependencies, and we use LSTMs to capture the long-term dependencies in the sentence. And the output of the textual encoding part is the x hat T that we talked about it. So short-term dependencies. Short-term dependency means that we have to reconstruct each word based on its neighboring words. So given the word vectors x1 to xn in a sentence, and their position vectors, the first word, the last word, the middle word, we gate each word vector with its position. So it matters if a word appears in the beginning of a sentence, in the middle of the sentence, or at the end. We pass it to a one-dimensional convolution, and we apply a gated linear unit on top of that as a nonlinearity. So gated linear unit is a popular form of nonlinearity in NLP. The way it works is that it splits its input into 2 parts, into 2 halves actually, and use one of them as gate on the other half. And we can stack these convolutional blocks to go deeper. In my implementation, I had 2 of these. So it goes deeper and it expands the receptive field of these convolutions. And finally, we get the output, which is the reconstructed word vectors. For the long-term dependencies, we use bidirectional LSTMs. So bidirectional LSTMs actually consist of 2 LSTMs. One of the LSTMs start encoding the words from the first word to the last word. The other one does the same thing in the reverse order from last word to the first word. And each time step t, we aggregate the output of each of these two LSTMs to reconstruct the x hat t. So we call it long-term dependencies because the x hat t is depending to all the words in the sentence from x1 to xn. So given the inaccuracy detection t star, our correct word prediction module suggests a correct word from the dictionary. So if our dictionary name is beta, it is basically a classifier on all the words in the dictionary. So given the detection scores, we are going through the details of the correct word prediction. Given the detection scores, we find using a softmax, we make probabilities out of them. And we have the encoded words as x of t, and we use a weighted average over the encoded words to encode the sentence. So we get one vector for this sentence based on the probabilities of inaccuracy and the word vectors. And then basically we have a simple classifier here, which gets the u of q, which is the encoded sentence, and gives us the suggested correct word. So what about the visual features? What about the video? So given a video, we have used two pre-trained networks, C3D and VGG19, and we extract features from both of them. And then using a temporal max pooling, we aggregate the temporal information of these features, and we return the visual feature. So given a textual input word 1 to word n, and the visual input, the visual features u of v, we name it u of v, we gate the visual features with each word. So it's like we change the visual feature based on each word, because some words may have a, like cat or dog, they have a simple appearance model. But some words like good, bad, is, the, they don't have any appearance, a specific appearance. So we have to behave differently based on the words. So the output of this gating process is the visual biases, word 1 to word n, and we call them v1 to vn. So we update the our detection formulation by adding the visual gated bias into our distance formulation. And then we add the visual features to our word classifier as well. So now we use the visual features to detect the inaccuracy and also to suggest the correct words. So let's look at some examples. In these examples, I show the result of the method if I use just text, and if I use text and C3D features. Like in this example, someone lowers her gaze and takes her bottom lip. So both of the methods could correctly find the inaccuracy, which is the word text, and suggest the correct word to replace bytes. People creep out from their hiding, beating. So the textual model is completely distracted. It detected the wrong word, but the text and video features, the model which used the visual features as well, is doing it correctly. Another example, he points to a large banner, then notices a pretty girl in the cap. So the visual, so again, the textual model is completely lost, but the visual features are helping to find the correct word, which is crowd. So it's basically see the crowd here and suggest the word crowd, but it fails to detect correctly. Again, another example. So what if we have multiple inaccuracies in one sentence? For example, in this sentence, for this video, if the sentence is, he looks his headphone off as he moves out of the front. So the accurate sentence was, he pulls his headphones off as he looks out of the window. So as you can see, 3 words here are wrong. Or another example, the landing indicates an incoming someone from Gold Coast Real Estate. The accurate is the display indicates an incoming call from Gold Coast Real Estate. So we show that with a small change in the test time, we can kind of solve the multiple inaccuracies scenarios as well. So the training remains the same, we just change the test part. So given the detection scores, we find the top K detections, the top K inaccuracy scores in the sentence. Then we want to encode the sentence based on the inaccuracy number M. So basically we have the word vectors, and we build a one-hot vector instead of the probability vector. We use a one-hot vector, which the index of the M inaccuracy is 1, rest is 0. And then again the same. We have a classifier to suggest the correct word for the M inaccuracy. So let's look at this example again. Inaccurate sentence, accurate sentence. If you use just text, this model was completely wrong to detect an inaccurate word. But when we use the text and video, it could correctly detect the inaccurate words. So let's talk about the data sets. We use MPI movie description dataset. This dataset comes with 158,000 videos. All of these videos are movie shots. They are from real movies. They have like 2 to 20 seconds length. And each shot comes with a sentence. The sentence is actually an audio description. Sentences are from 21,000 words dictionary, and each has 2 to 40 words in each sentence. So you can download the inaccuracy datasets based on the MPI dataset here under this address. And the way that we build the dataset for inaccuracy detection, we given a sample sentence and a target word to replace, we extract the part of a speech tags. For example, in this sentence, it comes out wearing a hat is the accurate sentence, is the original sentence, and we want to use to replace the word wearing to make it inaccurate. So we extract all the POS tags. As you can see, wearing is a kind of a verb. And we draw one sample from all the words which could be the same, could take the same tag, this, all the ing form of the verbs, basically. And we use a natural language words distribution to draw the sample because we don't want the rare words come up frequently. So we draw a word and the sentence becomes, it comes out being a hat. So this is the way that we generate the data sets to train the system that earlier I talked about. So as you can see, the frequencies of these words, inaccurate words, are similar to natural language. For example, you see they are mostly nouns, then different kind of verbs, then adjectives, something like that. So let's look at the results. So first, I show the inaccuracy detection results, just the first part. So how good we can detect it. The random chance is 8.3%. So then I show that experiments that I just use text. So first we use a commercial web app, this website, and we copy the subset of our test samples into this website, and we looked at it if it can detect the inaccurate word or not. 18.8% of the times it was successful. Then we use a vanilla LSTM, just one LSTM without our formulation, to detect the inaccuracy. It was 28%. Then we use one-way long-term dependency. So instead of the bidirectional LSTM in my formulation, I just use one LSTM. It became 58%. Long-term dependencies with bi-LSTM, 67. Convolutional n-grams without position embedding, 66. Convolutional n-grams, 69. And if I use convolutional n-grams and the long-term dependencies, and if I fuse them, I will get 72.5%. In the experiment that I use both video and textual information, if I simply concatenate the visual features with each word, I will get 72.8%. But if I use the visual gated bias technique that I showed you, I will get 74.5%. So about correction experiments. So in the correction task, we have to detect correctly and also replace correctly to say this example was successful. So as we can see, the accuracy is almost 0 for the random chance. Because the dictionary is big, then it has a very low chance that you detect correctly and randomly select the correct word to replace that word. So for the just textual experiments, the vanilla STM gets 17.2%, and our textual method gets 35.2%. For the visual and textual experiments, if we pre-trained our detection model and we use a fill-in-the-blank model, pre-train again, which use the visual features, everything, we get 36%. So just fill-in-the-blank is another research topic that, given a sentence with one blank in it, they learn to fill that blank. So our model, if we use just security features, 38%. And again, the same if we just use VG19. And 38.9% if we use both of these features. For the multiple inaccuracies experiments, here I show the value of k if we have 1 inaccuracy, 2 inaccuracy, 3, 4, and all. As you can see, about half of the sentences have more than 4 inaccuracies. And I show the number of test samples. For the detection task, the vanilla LSTM just get about 66% on all the sentences, 80% and 83% if we use both visual and textual information. So here I show two metrics. One of them is word-based and one of them is sentence-based. In word-based, I count each inaccuracy independently. But in the sentence-based, all the inaccuracies in one sentence must be detected correctly. Then I will count that sentence as a positive, as a success. So again, for the correction, our method gets just textual input will get 3%. If we use both text and video, we get 18%. We see a bigger jump here. Because when you have many inaccuracies in one sentence, for example, if your sentence has 10 words and it has 6 words inaccurate in it, then your textual encoding will be very noisy and very weak. So it makes sense that the visual features help more here. And for the same experiment, I show the mean average precision results as well. Thank you very much. I'm here to answer any questions. Also, you can send me emails if you have any further questions.